Mark Munens, and his presentation will be on numerical simulation of fatigue crack growth in straight lugs equipped with efficient structural health monitoring. Mark, you have 50 minutes for your presentation.
If the next presenter is not there, I can also use half an hour.
No, the next presenter
problem.
is here and he will continue after you. That's good news.
It's not handy on the left side, but okay. So thank you for to all of us to attend this presentation. I'm Mark Monens, and I come from the University of Brussels in Belgium, and it's really a pleasure to present here part of my research. And today, in particular, I will be dealing with fatigue crack growth with respect to structural health monitoring. So, a short outline of what I will be dealing about. Then. First of all, I will present, let's say, my view on why it's important to perform fatigue crack monitoring in structures in operation. And then I will show one implementation to do that we develop at my lab, and which is called the efficient structural health monitoring. And I will show a potential practical application of this system on a component, and we will see whether it influences or not the fatigue crack growth behavior of that component. So actually it's a bit a pity because I don't remember the author that used that word, but I find it really the most appropriate to describe the consequences of a fatigue failures, meaning namely that they are insidious. That means that they can occur actually without any warning that there is a problem, which is of course not very nice, and they have potentially tragic consequences. And to illustrate this, I've taken of course the well-known pictures. I've seen it quite a lot of times here in this conference of this Aloha 737, where part of the fuselage simply detached during flight, and it was indeed due to a fatigue crack growth. Picture on the right, let's say, is more anecdotic. It's main landing gear of general aviation aircraft that failed. And investigation has again proven that it was due to fatigue crack. And the reasons I selected these two cases amongst a lot of them is that they have common characteristics that illustrates that need of performing in situ, if you want, fatigue crack monitoring. Firstly, both of these aircraft, they were used very intensively. The Aloha 737, it was used for short flights between islands, which means a lot of frequent cycles in corrosive environment. And the general aviation on the right, it was used for schooling of pilots, which again means very frequent cycles of landing. And especially I can testify from my personal experience as a private pilot, student private pilot, the landings can be sometimes quite harsh. All that to say that the crack propagation rates in these two cases, well, they were higher, much higher than expected by the manufacturer, which is of course a danger. And both of these aircraft, they were actually followed by a strict maintenance scheme which was respected, and obviously the maintenance, classical maintenance, let's say, was unable to prevent the failure. And I'm an aeronautical engineer, so I've taken pictures from the aeronautical industry. But of course, I think all industries actually are concerned by fatigue cracks. And here I've taken another example of a quite dramatic accident, actually, where there were more than 100 deaths. And it was a German high-speed train that derailed while driving at maximum speed, which is of course not the best moment to have a derailment. And this derailment was due to a broken wheel, which was due to a fatigue crack that was not detected. So by all these examples, what I actually mean is that with the current technology we have, it seems that we are still not able to tackle efficiently and very reliably the problem of fatigue cracks propagating in structure, and this is why other approaches develop, and one of these approaches is structural health monitoring, or the comparison is often made with the nerve system because it's a bit alike. Let's say your nerve system, when you have no problem, you are living your life, everything is fine, and then suddenly you hurt yourself, you feel pain, and you know that it's about time to go to the doctor. Well, structural health monitoring, it's exactly the same, but on structures. You fit many sensors, let's say, on your structures so that you are able to monitor on real time, if you prefer, the actual quality of the structure. And in my lab, we are working at a specific implementation that we call the ESHM. And the working principle is very simple. I will explain it on a lab example. which is a rectangular beam under a 4-point bending test cyclic loading. And what you want is to be warned when a fatigue crack will develop into that beam. And to do that, what you do is that you include inside of that beam a void, if you want, or actually it's a bit long, so let's say a gallery. And this gallery is enclosed, meaning there is no contact with the atmosphere. And before the test starts, you put a different pressure in that gallery. So in this case, the initial pressure in the gallery is 0.5 bars absolute pressure. And you monitor the pressure in that gallery with the pressure sensors. So what happens when you have a fatigue crack that develops? It grows until the moment that it reaches the capillary. And at that moment, well, while your crack is opening, it's actually making a connection between your capillary and the open atmosphere. And then, in this case, you have a sudden pressure rise in your capillary, and you know that there is a problem. Of course, as you need to have an enclosed capillary into your structure, you are more or less obliged to manufacture it by additive manufacturing, and you could think of it as a limitation, let's say, of the system, but we see it in my lab in the other way around. Because additive manufacturing, it's very nice in the sense that it brings you additional geometric freedom, you have efficient material usage, etc. But it also comes with a certain number of drawbacks. And one of these is that if you manufacture a component with additive manufacturing, there are so many things that can influence the fatigue properties of that component that you are actually quite unsure of what the final fatigue properties are. And that I've taken here an illustration of a study of Mr. Loaders, where you can see, depending on the different post-treatments that are applied or the as-built conditions, well, the crack growth curves are totally different. So obviously a system such as the ESHM, it will not tell you what the fatigue properties of your component are, but at least you are sure that you will be warned in case of a problem. Now, I've shown, let's say, the working principle of the ESHM on a lab experiment. Now let's try to implement a potential practical application of it. And for that, I've chosen the case of a straight lug, because it's quite common case, let's say, quite common component in the aviation industry. And furthermore, as we are in Serbia, I decided to inspire myself, let's say, from work of Serbian authors, and particularly the author is here. I thank her very much again. So I've taken exactly the same load case as her, namely a straight lug with an axial cyclic loading. And of course, when you want to fit such a lug with the ESHM system, first question to ask is where to place the capillary. And of course, the answer is close to the regions where you have a high risk of crack initiations. And in that case, it's around the pin lug connection, let's say. So this is why you see here actually a cut view of the lug, and you see, maybe it's not very clear, I don't know, but you see all around, you see the capillary that has been installed, or to be some more clear, let's say, you have on the right a cut view of the top part of the lug, and you see the rectangle of the lug, of course, and you see the capillary. Of course, due to the fact that you include that capillary into your structure, you modify a bit that structure. So the question arises whether on that cross-section you will have kind of a different stress field. And the question is whether the capillary influence is so much that you will have an impact, let's say, on your crack propagation life. And this is in particular what we wanted to study. And to do that, we have created different Lugs models. So a model to serve as reference of a normal lug, let's say, so simply a lug without capillary, let's say, and then models with different capillaries, because of course you have certain design freedom with this ESHM. In particular, you could choose, for instance, the capillary diameter, and so we have created different models with different capillary diameters to see whether it influences or not the crack propagation life. And to do that, we have done a crack propagation simulation with the Morpheus software, which is an XFEM-based software. And well, XFEM, you have less problems, let's say, with the meshing, but it remains a FEM-based method, meaning that you have to work on a converged mesh. And to have a converged mesh, you have to be sure that your mesh is fine enough in the region of your initial defect. And yeah, that I forgot to mention, but the initial defect is always the same in all the load cases we have computed, namely a part-through crack in that upper region. And this is why you see that the mesh is so fine in that region. Alors, what are the results from the simulation? But, well, again, it might be not very clear, but let's say the curve, the most to the right, the blue curve, it's a curve for the normal lug, so lug without capillary. And you see that we come at a crack propagation life of about 32,000 cycles. And what you also see is that if you work with small capillaries, so 0.5 millimeters in diameter or 1 millimeter, where there is barely no influence of your crack propagation life, which is of course a good sign. You also see that if you start to work with much bigger capillaries, like 4 millimeters diameter, basically it's not a capillary anymore, you have a different structure and you have a drastic influence on the crack propagation life. Here you have a reduction of 20%. So this means that provided you work with small capillaries, it seems to be okay. But before we can be totally happy, remember that I explained in the beginning that the working principle is based on the fact that inside of your capillary, you have another pressure than the atmosphere. You can be under vacuum or under a high pressure. And again, the question arises whether this high internal capillary pressure, if you want, has an influence or not on the crack propagation life. And to do that, we have taken the same model. So this time only a capillary of 2 millimeter diameter, and we have applied different internal capillary pressures. And you see that compared to a normal lug, let's say, so without capillary, there is a difference, but this difference is only due to the presence of the capillary. Here it's a relatively big one, 2 millimeters, but you see that whatever the pressure you use inside of that capillary, you don't see any difference. And it's of course because at the pressure, let's say, loadings that we are working, so order of magnitude of 2-3 bars inside of the capillary, when there is not a lot of influence on your stress field, and basically you don't see any difference in crack propagation life. So to conclude, I hope that I have somehow convinced you of the importance of performing structural health monitoring on structures. In 15 minutes it's difficult to convince, but I've shown a possible solution to do that, and that we develop at my lab, and which is called the ESHM system. And I've shown that provided that you implement that ESHM system on effective component with small capillaries, well, you have no influence on the crack propagation life. Thank you very much.
Thank you. Let's start with questions. Yeah, because still 5 minutes left before next speaker. So if you have any questions, please. Microphone.
First of all, thank you for a very nice and interesting lecture. And maybe you said it, but I didn't hear the position of the capillary from the edge of the hole.
Yeah, I will try to use that one, but I'm not sure. Ah, yes.
Yes.
So, yeah, maybe it's not clear, but when you have such a lock, you want to know why it's positioned there.
What's the dimension of that position? How,
okay.
How far away from, and how you determine that position?
Yeah, that's a very pertinent question, because it was a problem that we had at the beginning. The problem being that, so you see here the cross section, and when developing the ESHM, we named that's very annoying. So we always speak as a reference of the distance between here, the bottom of the capillary, and here, which is actually this surface, so the pinhole surface, and this distance we call A. And there have been experimental tests done by my colleagues, Strenza and Mr. Indeldahl, to name only these two, on whether it was appropriate, which distance was appropriate with the crack initiation region, like you asked. And what they have noticed is that if you place the capillary too close, let's say, to the initiation region, you have a risk that the crack would initiate at the capillary itself, because there are two effects. First of all, you introduce a stress concentration, and so you risk that the stress actually around of your capillary is higher than the stress in your critical regions, which is of course not interesting. And furthermore, here I've drawn the capillary perfectly smooth, but since we do additive manufacturing, you have a bit of roughness inside of that capillary. So you have effectively a risk that the crack would develop from the capillary, and to avoid that they have performed experimental investigations, and they have shown for all the samples that they have tested that provided that this distance here, so the A distance, let's say, between the bottom of the capillary and your surface, or let's say critical zone, if this distance is higher than 3 millimeters, you have no risks anymore of crack initiation at the capillary. And here in particular, in all my simulations, this distance, whatever the diameter or so on, this distance was always 3 millimeters.
Thank you.
Okay, next question.
Did you measure some kind of stress concentration due to this capillary? Or, yeah.
Yeah, indeed, it's unfortunate, but it's unavoidable indeed to have some kind of stress concentration, but that's all the question, of course, of placing it at the right distance, is that, well, I don't have the values in head, but let's say that with the loading you have a maximum tensile, axial stress, let's say, of, I don't know, 250 megapascals at the pinhole connection, and let's say that in this region here, without the capillary, you have maybe, I don't know, 200. If you place the capillary, you will have a small stress concentration around the capillary, and instead of having 200, you have maybe 220. Indeed, you have a stress concentration. But your absolute stress value in the region of the capillary still remains inferior than the stress region, than the stress value in this region, and this is why you have no initiation at the capillary. You have indeed a stress concentration, but the effect is less than, the critical region remains the same.
Okay, thank you.
Next.
Your example is very interesting because the lug, if you look to the lug shape, the width of the lug defines if you have, if it influences the bearing stress or the net section stress. So I think I understand right, the capillaries around the entire hole in a certain distance.
Yeah, indeed.
Okay, then it would be good enough to have only a few let's say channels around the underneath, the hole underneath this square-shaped model or the other one.
Yeah, it's totally right.
Because the upper section is not loaded in any cases, right?
Yeah, indeed, I confirm.
Okay, thank you. And what I did not understand is if the capillary is clear, the pressure, but if a crack contact, if there is a contact and a cavity in between the surface, what is the warning system? How do you detect then the connection in between the capillary and the surface?
Well, yeah, maybe it's not very clear from that picture, I'm afraid, but here it's I knew that I'm always pushing on the wrong button, but so here in this configuration, in the lab experiments we have done, so you have here the maximum axial stress, so the crack actually starts here from the top, and you see that it develops, it grows until it reaches the capillary here. And what happens at that moment is that when it's loaded, your crack is open. So actually, if you zoom quite a lot in this picture, you would see the capillary and then an opening to the exterior, actually. It's like you would have a channel or a T connection between two pipes. You have really a physical connection, and so in this case you have air that is leaking from the atmosphere inside of the capillary. I will look if I have maybe a more clear picture of that, but I'm not sure.
I think I understand the mechanism, but how do you, if there is the connection from the atmosphere to the cavity, what is then the sensor? Or what kind of a sensor you use?
Sorry, I misunderstood your question. Well, when I said that there is no connection between the capillary and the atmosphere, I wouldn't say I lie, but actually there is one, but we close that one with a pressure sensor. So you have a pressure sensor that is always monitoring the pressure inside of the capillary. And this is what I try to illustrate here. So you are running your experiment, everything is fine, and then at the moment that your crack reaches the capillary, you have, like I said, air leaking from the open atmosphere inside of the capillary, and then what you see from your pressure sensor is that you have a sudden rise of the internal capillary pressure. And when you have such an important rise, you know that it's probably due to a fatigue crack that reached the capillary.
Okay, that answers the questions. Thank you.
Thank you. Next question. Okay.
And just a more practical question, how large is this pressure sensor and is it easy to apply to all kinds of structures?
You mean the pressure sensor or the capillary for the application on our structure? The capillary, you have to study a bit where you are going to place it, but from the moment you can print the structure, it's okay, you can place it. The
But
pressure sensor, it's of course always a question, and I must say I'm not a specialist in that because it's my colleagues that are busy in the lab. I do the numerical part, let's say, but what I know is that the biggest problem that they have with the pressure sensors, they use, I don't remember which sensor it is exactly, but it's quite small sensors, it exists, and I mean, you don't have to have a super high-tech sensor because to detect the pressure difference from here, in this case, 0.5 bars to 1 bar, you don't need a lot of accuracy of your sensor. The main problem is actually to be sure that the connection between the sensor and the capillary is airtight. That's the main issue, let's say. But by using Teflon or such kind of isolating paste, let's say, they manage to, so that it remains airtight, let's say, for the time of the experiment. But now it's something we are currently investigating. Are we sure that this type of connection remains airtight for the entire fatigue life of the component? That's the biggest problem that they have with the pressure sensor. But now for more details on the pressure sensor, honestly, I couldn't answer.
Thanks.
Sorry about this.
Thank you. Is this all? Okay, thank you for your presentation.